All right, good afternoon, everyone. And let's start. So first of all, for the homework which is due on Friday, I actually in my office hour yesterday, some students came to me and asked questions about that. I want to emphasize again, don't think about those problems overcomplicated. It's not complicated at all. It's just a kind of like direct application about what we have discussed in the class. Like I guess a lot of problem, quite a few students are stuck in with problem 1 or 2, right? There's some, there's some weird one univariable distribution, like you got like e to the power z square and have some sigmoid function. So our intention or expectation that you can apply the variation of lower bound of the sigmoid function we have introduced to the class. You don't need to re-derive that. Of course, if you want to do that, go ahead. You're very welcome. But what we expect is that, okay, you just plug in that bound, and you get a lower bound of your whole joint probability. And then you calculate the lower bound. You do the E step, you do the M step, you E step. You see that by plugging in that lower bound, your approximate posterior of Z is just a Gaussian, right? And then you do the M step, you optimize the additional variational parameters. That's it, right? So I feel like someone might feel like might consider it's too complicated. It's not complicated at all, just the application. Right? But again, if you still feel uncomfortable about this whole framework or didn't find or feel hard to start to apply this, just let me know, or later after the class, you can discuss with me. I'm glad to share with you the ideas, okay? Any questions so far? Homework 5. Homework 5 is gonna be released tomorrow. And due, I think it should be the, I think we'll still plan to allocate 2 weeks for that. That would be the end of the week after next week. So it's supposed to release homework 5 tomorrow, and you got 2 weeks to finish it. And don't worry, homework 5, the work amount is not large at all, but you do need to finish that because that's our last homework in this whole semester. Other questions regarding the homework assignments, the due and the project report, all kind of stuff? Okay. Let me find the right time. But basically, we try to give you as much time as possible, but we have the due to give the final grade. So I cannot give the extension beyond that point. That's a strict deadline. So other than that, we're trying our best to give you enough time. No, we don't. We got 44 students. We cannot allocate. I mean, for one lecture, you're not able to allocate 44 presentations, right? Other questions? Okay, and if you guys feel like you want more time to do the homework for like someone, I received some requests today, but so far I only received 1 request for the extension. I cannot do that only for 1 student, but if a lot of like 10 or 20 students are asking for that, we definitely can consider for that. Okay, but it looks like most of students feel comfortable doing homework 4. But just let me know if you have additional concerns or something like other things, okay? So let us continue with the neural network. So in the last lecture, we introduced what is neural network, what is general architecture, some kind of history review, and also we talked about the basic idea of the backpropagation, which is essentially the way to compute the gradient of the loss with respect to the neural network parameters. Right? We know that the neural network parameters are essentially those weights allocated or attached on those edges, right? So we introduced a very succinct representation in terms of matrices and vectors. Basically, all the neural networks can be represented in this way, right? You got the input layer, which consists of the input features, x0, which is vector. And then to generate the output or the input to the next layer, that means x1, right? Or x0 is the input to the next layer. If you want to get the output of next layer, which is the neurons in the layer, in the second layer, x1, we're gonna first do a linear transformation through the weight matrices, right? So you can imagine that you do this matrix multiplication, matrix vector multiplication, so W1, x0, and then you apply a nonlinear activation function per element, right? So element-wise. And then you get x1, right? This is where you calculate x1, which is the output of the second layer, right? The output second layer will fade to the third layer. And if you want to compute the output of the third layer, which is denoted by x2, we're gonna first do a linear transformation of the input again, which is now x1, right? And then apply the nonlinear activation function over each element, right? So get the output of the third layer, which is denoted by x2, you just keep doing that. Right? And once you get output of the second last layer, xl minus 1, then you generate the final output, xl, just through one linear transformation, right? And we usually don't apply additional nonlinear activation over that. And the reason is just to respect the tradition, nothing else. And that's it. And then that's how we compute, given a particular input feature vector x0, the output of the neural network or the prediction of the neural network. So we can index all the parameters in this sequential procedure like W1, W2 to WL by this calibrated W, right? And so you can see that essentially throughout this linear transformation, nonlinear activation, this series of such kind of things, you actually obtain a function, right? Your input is your x0, your output is the output of the neural network, and the computation of this function is kind of like a recursive composite of these operations, right? And then the problem is that although the composition, and meaning that you keep doing linear transformation, nonlinear activation, is kind of like very interesting patterns, but when you compute the gradient, because we want to estimate the parameters of neural network, right? You feed the data, you can construct a loss. The problem is how can we efficiently compute the gradient of loss with respect to each parameter, right? Namely, those matrices on the edges, right? So we're gonna use the backpropagation. So the backpropagation essentially is a smart way to leverage the chain rule. Again, we just want to give you a sense about that. You don't need to get to the detail about backpropagation because right now you have tons of libraries which can do backpropagation automatically for you. You don't need to implement it from scratch, but just you need to capture the idea. So basically, you're going to sequentially compute the partial derivative of your loss with respect to the neurons in each layer. And then you calculate the partial derivative of the neuron in each layer with respect to the weight matrices on those edges. Then you just apply the chain rule to calculate the partial derivative of loss with respect to the weight matrices. That's it. And they're going to use this backward order, in that by doing so, you can smartly catch all the intermediate results, and you just reload those intermediate results to compute your target gradient with respect to each matrices. You don't need to repeat computation. So calculating from the backward order is very important to achieve that point. Okay. And we will now discuss the details because backpropagation, this procedure is quite simple and quite mechanical. And if you're interested, you can take a look at my lecture video about machine learning, entry-level machine learning, CS 5350 or 6350. There are a lot of like more details about how do you do the backpropagation, but basically in our class, because our class is a kind of more advanced level, so we don't want to struggle with the details about specific details about backpropagation. And more important, nowadays you never need to implement backpropagation by yourself. You got a lot of like highly efficient and mature libraries to do the backpropagation by yourself, but automatically, not by yourself. Okay, so now we have wrapped up the general introduction of the neural networks. And then we'll talk about the general strategy to learn neural networks, right? We know we can use backpropagation to compute the gradient of loss. And in principle, we can use that gradient, any gradient-based optimization technique to learn those parameters or to update those parameters, right? But what specific optimization approach makes the neural network so popular and so successful? There are a lot of like optimization approaches, right? In the neural network domain, the most popular training or optimization technique is called stochastic optimization. And it is the stochastic optimization makes neural networks so powerful and also scalable to very large data set. And it turns out that neural network mainly work well under big data or large data, right? You need to make your optimization scalable, right? So what is stochastic optimization? So in general, stochastic optimization deals with some kind of objective which you want to maximize or minimize, right? This objective has the following form. So this is your objective L, and theta is the parameters you want to optimize by maximizing or minimizing the objective function. Let us just assume we're minimizing. Okay? So in the stochastic optimization literature, we're going to assume this objective function can be written as an expectation of some random function. Okay? So basically, you can view there is some function g, which is not only a function of theta, but also a function of random variable u. And then our final objective is take the expectation of this g function with respect to the distribution of u. Does it make sense? Right? And according to the definition, right, this we have reviewed this concept a long time ago at early beginning of this semester, right? And from the definition, this objective function should be written as the integral of this g function multiplying with the probability density of u and derivative of du, right? So this is the definition of expectation, right? So at the first sight, if you have such kind of objective function, it might be hard to solve. Why? Because usually people are interested in giving you a form of G, not the total form of this L. That means you have to do this integral by yourself to get the whole form of L. That means you have to do the expectation, calculate expectation by yourself, but derive by yourself. This is usually analytically intractable or even doesn't have any closed form. Then how do we maximize or minimize an objective function which we even do not know any closed form? Right? That's the problem of the that's the problem that stochastic optimization wants to address. Okay. So the key idea is that, so let me give you some concrete example, like maybe that will be better, right? Not too abstractive. So I can come out g of theta and u to be like logarithm theta square plus u cubic. Okay? This is my g function. And because the g function contains a random variable u, so this function is a random function, right? So now my objective essentially is to take expectation of my g function. Okay? I can take my p of u to be some Gaussian distribution. Right? Say maybe it's just a standard Gaussian distribution. So now can you tell me what's the form of this expectation? It's very hard to get. Actually, you don't have any analytical form of that. You can try to integrate a Gaussian with this logarithm guy, right? And derivative over du. Right? We don't have any analytical form. But we want to minimize this guy. We want to minimize this integral with respect to theta. Okay. It sounds very hard, right? So, and how to address this problem? Like, the key idea of the stochastic optimization is that, okay, I'm gonna look for a way to approximate the gradient of this objective function. So since I don't know the analytical form of this guy, so calculate the gradient of this guy seems infeasible as well, right? I don't know the form of that. How do I calculate the gradient of that form, right? But it leverages the structure of this objective. That is, it is an expectation of some random function, right? So you see that if you take the gradient of your objective function, you're essentially taking the gradient of this expectation, right? And in many cases, under some mild conditions, you can switch the expectation and the gradient. So that means you can move the gradient inside expectation. You can calculate the gradient of this random function. Remember, this guy is still a function of u, so it's still a random variable, right? So this guy, if you write it as some h function, right? It's still a function of theta and u, right? So it's still a random variable. And then you take expectation of h outside under p of u. Right? Does it make sense? Okay. Any questions so far? Okay, so then we call, given any instance of u, the gradient of this random function g with respect to theta as a stochastic gradient. Why is this called stochastic gradient? Because it's random. Because it's still a function of u, so it's a random variable. You take expectation of this stochastic gradient, you will get the true gradient. Okay? So this is also called an unbiased estimate of stochastic gradient. Why? Because you take expectation of this stochastic gradient, you can recover the true gradient. So why it's called unbiased. And in some cases, I mean, usually doing stochastic optimization, if you want to have some theoretical convergence, you usually require your stochastic gradient is unbiased estimate. But right now, I mean, in a few years, there comes out some research talking about the convergence guarantee for biased stochastic gradient, because in some cases, biased stochastic gradient is even easier to compute. Okay. So the key idea of the stochastic optimization is that I'm gonna just calculate stochastic gradient. I update my parameters with stochastic gradient. That's it. So this is a whole framework, general recipe for stochastic optimization. in the very first step, we're going to initialize our parameters for which we want to optimize, right? Then we go through many iterations from 1 to big T. And in each iteration, we're going to first sample the random variable U from its distribution P of U. So just got random instance of U, right? And then I plug in U into this function G. And then I just calculate the gradient of the function G with respect to theta. So now we got an instance of the stochastic gradient, right? Then we'll update theta by updating theta toward the negative opposite direction of the stochastic gradient. So this is like a standard gradient descent, except that we're going to replace true gradient by the stochastic gradient and multiply by some step size gamma t. Then we finish one update. And then we move to the next iteration. We're going to sample another value of U from P of U, right? And then we just calculate the stochastic gradient again and use that stochastic gradient to update theta. We keep doing this until some maximum number of iterations have done or some kind of convergence test has passed. And then we return our theta. Any question regarding these algorithm steps? Everyone's comfortable? It's pretty straightforward, right? So, yeah, the gradient is random variable. Yeah. That's a very good question. I will come to that later. But you're going to use the same framework. But except that in that stochastic variation inference, the theta is not theta here. It's actually the mean and the variance in your posterior distribution. Yeah, variation of posterior distribution. Any other question? Okay, that's great. So basically, I want to give some kind of metaphor for this procedure, right? So if you think of the gradient descent, suppose this is your optimum, right? You initialize from arbitrary place, like theta 0. If you use gradient descent, you actually keep working toward, keep moving toward the optimum, right? And the more rigorous speaking, if you can draw the contour of your objective function, it's always perpendicular to the contour. It's called steepest descent. But anyway, if you apply the exact gradient descent, it will just give you kind of like quite straightforward path and move toward the optimal. However, if you're doing stochastic gradient, what does it sound like, right? What does it like? So it's like a drunk driver. Remember, every time you just sample U, right? And you just plug in it, your gradient, your stochastic gradient is not accurate at all. It's just like, statistically speaking, on average, it is aligned with the exact gradient. But for every particular instance, it might be quite far away from the true gradient. So if you look at the trajectory of the stochastic gradient descent, it might be something like that. So it's like a drunk driver, you randomly drive for a while, right? North, south, northwest, southeast, and keep doing that. However, you can guarantee that finally you still arrive at your house. That's a good thing, as long as you can ensure your step size. Every time you random pick up a direction, you drive for a particular distance, right? And then you random pick up another direction, you drive a particular distance. As long as you ensure the sequence of those distances along each random direction satisfies some conditions, it guarantees that you're gonna arrive at your house finally. That's very good. That's a very well-known theorem in stochastic optimization literature. If you mean you plug in you replace u by the expectation of u? Well, you can do that, but there's no guarantee it's going to converge. Because this is not, because the expectation of the gradient of u is not necessary to be the gradient of the expectation of the gradient of the random function where u evaluated as expectation. It's not necessary. It's kind of biased estimate. If you want to show the convergence, it will be a lot more difficult. So, but anyway, hopefully this metaphor or this analogy can give you a sense how stochastic optimization works, right? So, and then in what kind of conditions or what kind of setting of these distances or step sizes can ensure even doing this random or wild driving, we can still guarantee to arrive at home, right? So we need to restrict the step sizes. So remember, our step sizes are just the sequence of numbers, right? Positive numbers, gamma 1, gamma 2, gamma 3. Right? You can view as a series, right? So we need to guarantee that this sequence of the step sizes are square summable, but not summable. What does it mean? So first, of course, we need step sizes that are positive. That's basically if you want to minimize, of course, you need to make your step size positive, and then you move along the opposite direction of the gradient, right? because the direction of gradient is actually increase the function. And secondly, this is about square summable. Square summable basically means the sum of the square of step sizes over t from 1 to infinity is bounding. So if I write it more formally, it should be something like that. Gamma t squared abounding. This is called square summable, right? And then the third condition is called not summable. What does it mean? If you direct sum over step sizes from 1 to infinite steps, it will diverge. So basically says this is not bounded. This is just infinity. And if you use these conditions to prove the convergence guarantee, there's a very nice and elegant proof I studied during my PhD study. I do use a lot of like analytical mathematical analysis techniques, but the basic properties about sequence series analysis. But here we don't want to go to the proof details. We just want to give you the intuition. What do these two conditions mean? Right? So first of all, so suppose this is your function, right? This is some optimal you want to arrive, right? So the first condition, namely square summable, it just means your step sizes are not too large. So imagine if your step size is too large, it is possible that you kind of like jumping around and then just jump and never go down to the basin. So the square summable is to avoid you arrive at this kind of cases. And then what does the not summable mean? Right? Not summable mean is to ensure at the same time, ensure that your step sizes are not too small. If your step sizes are too small, what will happen? Like you starting from here, just stuck here, like start in the middle, and you never go down. So you can see these two conditions kind of asking you to make a right choice of the step size sequences, which are not too large, which are not too small. Under these two conditions, then it guarantees that finally you are gonna arrive at the local minimum of your objective function. Does it make sense? Does this intuition make sense? Any question? Yeah, yeah. It needs to get smaller over time. Otherwise, you cannot make sure your square summable is satisfied. If it doesn't get smaller, well, this guy must be unbounded, right? I won't be bounded. But you shouldn't make it too small. Make it too small, that means this guy is bounded. Then that means with probability 1, your update will just stop in the middle. You won't go further. Any question about this intuition? Everyone is comfortable with this? Yeah. So then people would ask, what kind of scheduling of this gamma t step sizes can satisfy both conditions, right? There are a lot. For example, very simple, there are two simple cases listed here, right? You can check by yourself. This is another practice of the calculus, like calculus 1 or calculus 2, whatever, right? And but more than stochastic optimization algorithms are not using this. They use the so-called momentum-based approaches. So basically, you can imagine your theta usually is very high dimension, right? It is a long vector, like neural network. Neural network, you have a lot of parameters. So deep neural network may have like 1 million parameters, 2 million parameters. You don't want to use one step size for every element in your theta vector, right? You want to do some kind of smart step size adjustment for different elements. I mean that for different elements, you're gonna have different step size. And then your gamma t will be a vector as well. And they have a bunch of different ways to adjust gamma t element wisely. And they introduce some ideas called momentum. It's like the gradient descent, ODE system will, and the gradient descent is like you push a small ball in the surface. It's like Hamiltonian system, but this is not Hamiltonian system. It's just the ODE. And then when you want to make want to arrive at this basin as quick as possible, they're going to consider not only the gradient, because gradient is actually the speed, the velocity, right? You also want to talk about the momentum. Right? So a lot of approaches, they invented different types of momentum and how do you merge the previous momentum and the current momentum, and you get a current momentum, then you regularize the step size and so on. So a lot of such kind of techniques. So right now in the neural network domain, I would say most popular approaches include ADAM, AutoGrade, Eta Delta, and etc. Especially ADAM, it almost the by default choice of the stochastic optimization approach. But again, in your research or project homework, you don't need to implement ADAM by yourself. Those implementations are provided by nearly all the neural network libraries. You just need to call those algorithms. Okay, so far, any question? This is just a general introduction of the stochastic optimization. Now we want to relate it to the most common usage, especially in neural network training. Okay, so why stochastic optimization is important, right? And why it is viewed as the foundation of the modern neural network training, right? So the reason is that the laws of the neural network is usually has an additive form. So imagine you got like 1 billion data points, right? For each training example, you got one loss, right? You use your neural network to make a prediction, to predict a particular label like yn, right? And then you calculate the difference between yn and your prediction to come out a loss. It could be square loss, it could be cross entropy loss, whatever, right? And then suppose you have a lot of training examples. You have a big N training examples. N could be 1 billion, right? If you want to compute the whole gradient, the exact gradient of your loss, that means you have to go through 1 billion data points, right? For each data point, you compute the gradient of the loss for that data point. You add them together. That's really, really expensive. Okay? So let me write down, it will be, you need to go through each training example. For each training example, you calculate a loss, you calculate gradient of loss using backpropagation. You have to run backpropagation for 1 billion times. Add them together, you get your full gradient. Then you apply your gradient descent approach. Okay? That's really, really slow, given that the modern neural networks are even larger, right? You got 1 million parameters, 2 million parameters. That's very, very common. So you can imagine this is too slow. Right? So people won't use this type of method. Right? So now how can we make our optimization more efficient? That's where the stochastic optimization can play the role. Right? Because if you look at the additive form or summation structure of your loss, we can view it alternatively as a stochastic objective. Namely, we can view it as an expectation over loss function defined on many batches. Can you see this, right? So if you can partition the training examples, okay, this is a this is a whole training example, right? So I can partition them into many, many small mini batches. Right? So I can come out a random variable u, and this random variable is just to uniformly pick up a mini batch. Okay? So suppose I got 1, 2, 3, 4. I got like 10K mini batches. So I got a random variable u, which can take value from 1 to 10K. And the probability of u take any mini batch, say 1 or 3, is just 1 over 10K. Okay? The total number of mini batches. Okay? Then we can come out a loss function as the summation of the loss over each mini batch, then multiplied by this ratio. That's the total number of examples divided by the size of mini batch. Right? This is all the same if we check out the math, right? So now we can write down this guy in this way, right? And in the outer level, you just go through each mini batch, u from 1 to big N over B. So in our previous example, we assume big N over B is just 10K, right? 10K mini batches. You go through every mini batch, and then you multiply this factor B over N, and then inside each mini batch, so here this BU are the mini batch, right? Inside each mini batch, we calculate the loss of each example on this mini batch times this N over B. Right? This is the same thing. Why? Because B over N, N over B, you just cancel, right? Just 1. And then you just sum over the mini batches in the outer level. Inside each mini batch, you sum over each examples. So overall, it is equivalent to sum over every example in the total, in the whole data set. Does it make sense? Right? So now, the decomposition, the further decomposition, one more level decomposition can, what does this one more level decomposition can tell us? It actually gives us another view. That is, we can define the summation of the loss over one particular mini batch as a particular loss function, right? As a particular loss function, let me denote it by L hat, which is function of the W and also the index of the mini batch, right? And in the outer level, you just go over all possible mini batches, right? So in the outer level, because you go over all possible indices of mini batch, that means U from 1 to N over B, and you times N over B. So overall is essentially an expectation. Right? It's like you're gonna take expectation over this L hat WU, right? Because P of U is a uniform distribution, right? So if you calculate expectation, we know this is just a discrete distribution, just a sum over all possible values you can take, which is U from 1 to N over B, and times the probability U takes each value, which is just B over N, and times the value, the associated loss on that min batch, right? And then you just replace this L hat by the thing we just defined, right? We go back to this guy. In other words, we can view the total loss, I mean, the loss over the entire training set as an expectation of some reskewed loss on the random mini batch. Does it make sense? Okay. Anyone feels uncomfortable? Because this is really important. I want to emphasize everyone feels comfortable. I want to make sure everyone feels comfortable. It's just to rearrange the training examples into different mini batches, right? Then you just go through every mini batches. And then you plug in this additional factor, B over N, and then you multiply N over B inside the loss of each mini batch. The reason of doing so is that when we have this additional factor B over N, it can be viewed as the probability of selecting one mini batch, right? And then this whole summation can be viewed as you're going to take expectation of this reskewed loss on the mini batch. Any question? Mm-hmm. You just random partition them. You cannot let one data point goes to two different mini batches. You have to partition them. For example, if you want to do this, right? Suppose this is your data set, right? You're gonna partition your data points into those mini batches. And the whole loss can be viewed as, okay, I'm gonna first random pick up a mini batch, then calculate the loss inside this mini batch. Of course, I need to reskew that. And then I do the expectation. That will be exactly the same as the loss over the entire training set. Okay, does it make sense? It's just a mathematical trick. You just or if you still feel uncomfortable, try to use this definition. Try to calculate that, given that your P U equals to G is B or N. Try to calculate this expectation. You see exactly, it'll give you this, the original entire loss. Okay. So now that we can view our total loss as an expectation of the residual loss over the random mini batch. Now, each time, as we mentioned in the stochastic optimization, I don't need to calculate the exact loss, right? I just need to calculate a stochastic loss, which is on a particular mini batch, right? Because computation of mini batch is much, much cheaper than computing on the entire data set, right? So every time I just random pick up one particular mini batch, which may consist only like 50 examples, 100 examples, I calculate the stochastic gradient and I use that gradient to update my model parameters. It is a lot cheaper. I don't need to wait. I go through every training example, calculate all the calculate their loss and add them together, right? That will be a lot more expensive. So any questions so far? Yeah. That depends on the property of the loss. Like if your loss is a convex function, well, no matter what kind of optimization, as it converges, it arrives at the same point. But if your loss is not convex, it has many local minimum, and it depends on where you start. Using stochastic optimization, you might start here. Using other optimization, you might start here. But usually, we're going to guarantee that you are going to arrive at some local basin of the function curve. Yeah. It's just to ensure that your expectation is exactly the same as the original parameter. Why? Because remember, your P of U is B lower N, right? If you want to calculate this guy, and if you calculate this guy, right? This essentially is to take U from 1 to all possible indices of the mini batches, right? And you multiply the density of P of U, which is B over N, right? And then inside each mini batch, you got to have this N over B to cancel it out. Otherwise, you kind of like change the loss. Okay, any other question? Great. So that means if you apply the stochastic mini batch optimization in general, that's how we train neural network. So we can say now in this step, it becomes sample a mini batch, right? And then we calculate the stochastic gradient under the mini batch, which is essentially to calculate the loss of the training examples in that mini batch and calculate gradient, right? But you have to rescale it by N over B. Right? And then you update your model parameters with the stochastic gradient based on that mini batch. And next iteration, you're going to sample another mini batch. You keep doing this until you your optimization is done. Whatever stopping criteria are met. Okay, and in practice, you might have seen like people usually don't do this. It's not. They just random partition and they just go through every mini batch sequentially. I would say that is not exactly right, but people usually do that. Maybe this is more, this is simpler and convenient, right? But if you want to show, okay, this is like a rigorous, guaranteed stochastic optimization, you have to sample the mini batch every step. Now comes to the main topic, right? Bayesian neural network, right? So how can we plug in probabilistic modeling into the neural network? So it's pretty straightforward. Instead of viewing each weight matrices or elements here as some constant, right? So in the Bayesian neural network, we usually assign some prior distribution over the weights on those edges. And that's it. That is Bayesian neural network. And you can imagine that now we will like W1, W2 to WL as random variable. And then given any instance of those random variables, your output of neural network essentially is a random variable as well, right? Because it is essentially a function of those of W's. Okay? So because W is random variables, and then the FWX0 will be random variable as well. And then how do we write down the joint probability, right? So usually, this is the general form of the joint probability of a Bayesian neural network. So we got n data points, right? You got xn, yn, you have this big n pairs of input and output. So the joint probability will be, okay, first, we're gonna have some prior over the neural network weights, or to sample the neural network weights. Then given those weights, we're gonna sample the output, right? And of course, given those weights, how do we sample output? We're gonna first generate the neural network output, which is f of wxn, and given that, sample yn. For example, if yn is continuous, then the most commonly used choice is just the Gaussian distribution, right? Sample yn, which is simply yn and wxn as a mean, and you got some variance parameter, right? Then that's it. This is the definition of Bayesian neural networks. Any questions so far? That depends on how you specify W, right? So if you specify, if you get different value of W, of course the output will change. I would say you will will the output as a random variable. That means it can take a lot of different values. It has a distribution, right? Because it's a random variable, it has a distribution. So we're interested in, given the data, what's the distribution of your output, right? It could be some Gaussian or whatever other complicated distributions, but it's no longer a point. Other question? Okay. So now, what are the commonly used priors for the weights? Okay. So the most commonly used prior are just individual Gaussian. So assign a standard Gaussian prior over every element in those weight matrices. That's the most common choice. But sometimes you might want to add other priors, like you want to shrink some weights. Then you can apply some sparse priors, like spike and slab prior or Hausdorff prior. Those prior kind of encourage the weight value to be centered around 0. And then during the posterior inference, we still want to estimate the distribution of those weights given data, right? And if you have some sparse prior, we would like to expect the posterior distribution, many weights are concentrated. Their distribution is concentrated at 0. So you can prune the network. Right? That's also a hot topic in neural network research, how to compress the network. And what is the likelihood that is often used in Bayesian neural network, which is very similar to like general linear models. Like If your output is a continuous variable, then oftentimes we just use Gaussian, right? And we might need to add some prior over the variance, right? Like using some conjugate prior, like inverse gamma distribution. Like this, we're all very familiar with. If your problem is a classification problem, like a binary classification problem, then Yn is either 0 or 1. Then you can use Bernoulli likelihood. Okay. If you're doing multi-class classification problem, this is very common in image applications, like image classification. You might have like 1,000 categories to predict. Then we use categorical distribution. And to parameterize the parameter of the categorical distribution, you really take exponential of your output. So basically, if you have a categorical output, okay, so your output will be a vector rather than scalar. So each output, suppose you have a k output, then you have k categories. Then the neural network usually predicts k scores, and each score measures how likely it should belong to category, a particular category. And of course, we want to turn these k scores into a probability. And the commonly used methods is that we take exponential of them and then normalize it. This is called softmax. Okay. Why do we take exponential? Any thoughts? Why do we take exponential? Yes, exactly right. We want to come out a probability that you take a particular category. This probability must be positive, right? But your score, your raw score predicted by a neural network could be negative. So you have to make sure it is positive before you do the normalization, right? That's why people usually take exponential. Of course, you can take square if you like. But I would say taking the exponential of your score and then do the normalization is the most common choice. Any other question? Okay, great. So now we have use a probabilistic framework to describe neural networks, right? So once we have a Bayesian neural network, what is our goal? Like, what is our goal in the training? What is our goal in the prediction, right? So basically, we have two major goals. First, we want to estimate the posterior distribution of neural network weights. So we know that neural network are parameterized by the weights, right? So you assign the prior over the weights. Then, given the weights, you can give the prediction of the give the prediction over any input, right? So the prediction itself will be a random variable as well. So basically, this is a valid joint distribution. Given a bunch of training data, is valid to ask what is the posterior distribution of the weights, right? And especially if you assign a sparse prior over W, when you calculate posterior distribution, you're asking which weights can be pruned, right? So that we can reduce network, we can compress network, right? And the second goal is to estimate the predicted distribution. This is the same as the general goal in the Bayesian inference, right? So according to the posterior distribution of those weights, right? And then given each particular instance of the weights from the posterior distribution, what is the probability you predict a particular value Y star? Right? You want to integrate out all possible choices of W to give a more robust prediction. Right? That's our goal of performing, of calculating predictive distribution. Okay. So far, any questions? Is everyone good with this Bayesian framework of neural networks? It's kind of like smooth transition to neural networks. Right? But all our previous knowledge, all our previous principles can apply here as well. Okay, so now we're going to introduce how do we conduct variational inference with Bayesian neural networks, for Bayesian neural networks. There are a few methods, but here we're going to introduce the simplest one and yet most widely used one. And basically, based on, using that principle, you can modify it very easily and do whatever inference for other types of neural networks. So this algorithm is called Bayes by backpropagation. And the key technique used inside this Bayes by backpropagation algorithm is the so-called reparameterization trick. And this is really, really important. And but I want to emphasize it's not only applicable to neural networks, it's actually applicable to almost all the probabilistic models. So it's very important. And but we want to use neural network as an instance to illustrate the idea. Okay, so let us consider the posterior inference of a Bayesian neural network first. We have talked about two major types of approximate inference techniques. One is called variational inference. One is called Markov chain Monte Carlo sampling. Right? We mentioned that if you really do some good and ideal posterior estimation for neural network, please use Hamiltonian Monte Carlo sampling. That's really good. However, in many cases, especially when the data is large, doing Hamiltonian Monte Carlo sampling is really, really costly and really, really slow. Remember, if you do the Tropoli-Hastings test, you have to compute the whole joint probability. Once you compute the whole joint probability, you have to compute the likelihood for every training example. Right? Suppose you have 1 billion training examples. To accept even one proposal, you have to calculate the joint probability over this 1 billion training examples. So you can imagine it's really, really slow and really, really costly. So in many pragmatic scenario, we would rather use more crude approximation, that is the variational inference. Right? The problem is how can we apply the variational inference? Right? So first, as we discussed before, right? To perform variational inference, we need to introduce the approximation of the posterior, right? Which we call variational posterior. Right? And use that variational posterior, we construct a lower bound of the model evidence. Then we maximize the lower bound of the model evidence to optimize the approximate posterior, right? If you still remember, like we restrict our approximate posterior in a particular family, that might be Gaussian, and then we just maximize the evidence lower bound to find the best approximate Gaussian, which can be as close to the true posterior as possible. Right? That's the idea. So here, what kind of posterior form would we like to use? And we often use fully factorized Gaussian. It's simply because it's convenient and easy. And of course, it's kind of crude approximation because you're assuming your posterior is not only fully factorized, but also has some restricted form, which is Gaussian. But let's just sacrifice the accuracy first. Let's just choose this crude approximation. That is, we assume our variational posterior is factorized over each element, every element, and for each Q of Wi, we parameterize as a Gaussian distribution. And here we have two parameters. One is the mean, and the other is regarding the variance. However, we want to make sure our variance parameters is always positive, right? I don't want to put kind of like a constraint, explicit constraint. Right? So we can reparameterize your variance in this term. Like you take a logarithm 1 plus exponential to some guy. This guy will guarantee to be non-negative, right? To be always positive. Then you just plug in your parameter inside this. This is often used trick to ensure some positivity constraint. Then what you need to do is just to optimize mu I and rho I. You don't need to worry about the range of rho I. Rho I can be positive, can be negative, can be whatever values. Right? Because once you take exponential, then you take a logarithm, exponential of rho I plus 1 is always give you a positive variance. And then we're going to use this fully factorized Gaussian distribution to construct our variational model evidence lower bound. Right? So according to the definition, the variational model evidence lower bound is defined as the expectation of this log fraction, right? The log of the log fraction between the joint probability and your approximate posterior. Right? And your parameter for your variational evidence lower bound will include all those mean and rho i's. And then your goal is to maximize this variational lower bound so as to find optimal value of those mu i's and the rho i's. Okay, that's the global variational inference, right? And if we take a look at the specific form of this variational lower bound, it has the following form. So it is expectation of the log prior of each wi under q of wi, and this is the entropy of each q of wi. And this guy is going through every training example. Mm-hmm. Yes. Yeah, you can do that as well. Yeah, that also worked. But this is a choice of this space by backpropagation. You can come out other choice. You can even take it to be rho I squared. But I mean, different parameterization can lead to different performance. But once you plug in your Q of W, it will give you this structure. Right? So where does this two from? Right? So if you take a look at this term, right? So we got Q of W, logarithm of P of W and Q of W. Right? And both P of W and Q of W are kind of factorized. So this guy equals to P of Q of W, logarithm of P of W over Q of W, right? And then both the numerator and denominator is kind of product over each individual probabilities. So when you simplify it further, you can just go through each element y. And this guy is Q of W log Q of Wi, right? And this is the definition of entropy. That's where this term comes from. And good thing is that the entropy of a Gaussian distribution has a closed form, and you don't need to memorize that. You just check out the Wikipedia. Right? And the expectation of this is analytically tractable as well. You can do it by yourself. It's log Gaussian. If you use standard Gaussian, it's just a half Wi squared, right? You take expectation of Wi squared under Q of Wi. It's pretty straightforward. So, as we just mentioned, right? For the first expectation, it is analytical for Gaussian prior. For the entropy term, this Gaussian entropy is here. It's analytical. Then there is one issue. That is the expectation of the in the middle, right? So we need to take expectation of the log likelihood for each data point, right? So log likelihood for each data point is log P of Yn given the prediction of Yn if the input is excellent, right? And remember this prediction or this output of the neural network essentially is very complicated function of W and Xn. So if you take expectation outside, it doesn't have any closed form. You don't know how to take that. Does it make sense? It's like your whole log likelihood is a very complicated function. Let me denote it by HW and Xn and Yn. And W are so complicated and so complicated that coupled inside H. So you take expectation of W of H on the Q of W, you don't have any closed form. How can we address this problem? Maybe it's okay, but just connect to what we just discussed. Yes, exactly right. Remember, for stochastic optimization, it is used to address this tricky form of the objective function if it can be written as an expectation of something, right? Right. The benefit is that, okay, as long as I can generate a sample of U and then plug in this, I just compute the, maybe I should use G here. I just sample instance of U, right? And then I just calculate the gradient of G evaluated at this instant of U. Then we get a stochastic gradient, right? I only need to estimate, I only need to update my parameters with this stochastic gradient. I really don't need to compute what is the exact gradient for that because it is infeasible to compute. So here we met the same situation, right? We don't know the form of this whole expectation. But we can will the whole objective, right? This guy as an expectation under Q of W, right? So I can just calculate stochastic gradient. That's some kind of stochastic gradient inside here, right? Then the problem should be resolved. That's where we can apply stochastic optimization. But here, there's a still problem here. It's not a naive application that can address the problem. To see that point, right? If we take a look at this particular expectation, that is, we pick up a particular training example, Xn, Yn. So this is the log likelihood of Yn, right? Given your prediction made by the neural network, right? You take expectation outside. If you just sample some instance of W according to your current Q of W, and then plug in this log likelihood, then you calculate the gradient of the log likelihood. It will simply give you 0. Okay. Why? Because your output has already been there. Right? Your parameters itself is actually doesn't appear inside this log likelihood. Right? Once you calculate instance of W, right? You generate instance of W hat. Your posterior mean and posterior variance never appear in your log likelihood. So you calculate gradient of this log likelihood is simply 0. Oops. Oops. What's it? Oops. That's weird. All right, I think probably was just stop here. We only have 3 minutes, but is there any question regarding the problem we have discovered? Right. So there must be some weird thing happen here, right? And why doing that is not correct. Let us leave that problem on next Tuesday, and then we'll give a mathematically justification why doing that is wrong. Okay, thank you. I apologize for this accident. What happened here? It says the video is still recording. I don't know what happened to this Zoom. It looks crashed. But anyway, let me just shut down because I'm really not sure if it's still